Sound waves filmed within diamond crystal in a first. Source: Interesting Engineering. Date published, October 2023. The research could help to further ultrafast imaging of solid materials such as metals, ceramics, rock, and bone. In a first of its kind, scientists have now observed sound waves moving through a diamond crystal using a novel X-ray method.
Very darling, she's a terrible shot. That was unexpected.
A group led by researchers from the Technical University of Denmark employed a technique using an X-ray microscope that could see acoustic waves within atom-sized crystals with sub-picosecond precision. This enabled the team to see how mechanical energy thermalizes across timeframes ranging from picoseconds to microseconds by directly visiting the creation, propagation, branching, and energy dissipation of longitudinal and transverse acoustic waves in a diamond. The findings of this process could pave the path for rapid imaging of solid objects, including metals, ceramics, rocks, and bones. Characteristics of materials. An essential component of materials science, geology, and solid-state physics is understanding the structural dynamics of crystalline solids. But many materials have intricate structures that simultaneously display dynamism on several length and time scales. According to the team, solid crystalline materials, including metals, ceramics, granite, and bone, are notoriously challenging to represent. They consist of grains, domains, and faults and are hampered by various opposing forces acting on them at different levels. Scientists have utilized highly specialized X-rays to simulate these materials, and they have progressed to the point of defining materials with a resolution as low as 100 nanometers, more than 500 times thinner than a human hair. Another factor is that the processes occurring in these materials take place over time. Scientists have not been able to see them in more detail than milliseconds to seconds. However, some functions within crystals, such as shape change or heat transmission, happen very quickly. These things are related to how the atoms in the crystals are arranged and move. They often happen in microseconds, sometimes even pico or nanoseconds, 1 trillionth/1 billionth of a second, respectively, said a media statement. Novel methods. The limitations prompted the team to employ X-ray diffraction-based imaging methods that help them see these changes in 3D. However, scientists say until now, it has been done quickly enough or without causing any harm to the crystal itself. The new methods promise to do it faster and non-invasively and will work for many crystals. Here's a video of different types of sound waves traveling and reflecting off the surface of the crystal. Dispersion and attenuation, weakening of the wave, over a microsecond timescale. To do imaging at the speed of sound, it was necessary to build an entirely new microscope at the end of a 3 km long X-ray free electron laser, XFEL. It is not a given that you'll succeed when aiming a 3 km long X-ray source through multiple lenses and onto a sample that is 1 mm across, while you hope to see a sound wave that only exists for a millionth of a second. Our hair-thin X-ray and optical laser beams had to meet on the M-sized single crystal diamond sample with a better timing accuracy than a nanosecond before the first data could be acquired. But we did it, and I believe these results will inspire a plethora of new research, said Henning Friis Paulsen, a professor at DTU and an author of the study. With this technique, researchers could look at various ultrafast structural phenomena that have eluded researchers for a long time. Geoscience, materials research, and solid-state physics all benefit from the ability to see structural events on timescales less than a microsecond. The team highlights examples of how it inhibits comprehending the mechanisms involved in thermoelectric materials, photonic crystals, metamaterials, or even soft materials like parylene and hybrid perovskites. Testing seismological models of how sound travels in planetary materials may also benefit geoscience. The details regarding the research are published in the journal PNAS. Abstract. The dynamics of lattice vibrations govern many material processes, such as acoustic wave propagation, displacive phase transitions, and ballistic thermal transport. The maximum velocity of these processes and their effects is determined by the speed of sound, which therefore defines the temporal resolution, picoseconds, needed to resolve these phenomena on their characteristic length scales, nanometers. Here, we present an X-ray microscope capable of imaging acoustic waves with sub-picosecond resolution within atom-sized crystals. We directly visualize the generation, propagation, branching, and energy dissipation of longitudinal and transverse acoustic waves in diamonds, demonstrating how mechanical energy thermalizes from picosecond to microsecond timescales. Bulk characterization techniques capable of resolving this level of structural detail have previously been available on millisecond time scales, orders of magnitude too slow to capture these fundamental phenomena in solid-state physics and geoscience. As such, the reported results provide broad insights into the interaction of acoustic waves with the structure of materials, and the availability of ultra-fast time-resolved dark-field X-ray microscopy opens a vista of new opportunities for 3D imaging of materials dynamics on their intrinsic sub-microsecond time scales.